Hello, and welcome to the Space Telescope Public Lecture Series. Tonight, Hubble from Space, an integral field spectroscopy from the ground, seeing both the forest and the trees, by Dr. Marc Sarzi of the Armagh Observatory and Planetarium. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute in Baltimore, Maryland. And as always, I want to give special thanks to this tech team, and I call them amazing every month, but they really are amazing. Thomas Marufu and Grant Justice, who do the webcasting recording and get it out to you on YouTube. Our upcoming talks next month, another sort of deviation from our norm. We're going to go into neutrino astronomy. All right. Do you know that you can do astronomy with neutrinos? Well, if you don't, well, then definitely show up in April when Marco Santander of the University of Alabama will tell you how you can do astronomy with neutrinos. On May 3rd, the nebulous effects of supernova imposter syndrome, a title that's probably trying to be a little bit too clever, but it's by this guy, Frank Summers, who has the same name as me, so he's probably just trying to be clever for this stuff. What he's actually talking about is Eta Carinae, a supernova imposter that, due to its explosion, created a nebula. In June, we will have Understanding the Formation and Evolution of Galaxies by a wonderful speaker, Cameron Hummels from Caltech. You want to find out about these talks and more, go to our website, which you can find at stsci.edu/public-lectures. You will have pointers to our webcasts, as well as the easiest way to subscribe to our email. There are lists of our upcoming lectures. And if you click on these lectures, you get the full information about it, including the speaker, title, and description, but also, after it has been recorded, the links to the STSCI webcast, as well as the webcast on YouTube. Our email list, well, the announcements, as I said, easiest just to sign up on the website. As an alternative, you can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word, Hubble Space Telescope, and you will get notices of our new videos, as well as reminders of these live events. As always, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media accounts are for the Hubble Space Telescope, the Webb Space Telescope, and for the Space Telescope Science Institute, and they're available on Facebook, Twitter, YouTube, and Instagram. I myself only do a tiny amount of social media, and can find me as Dr. Frank Summers on Facebook or Twitter. The news from the universe for March 2022. Our first story, as it has been the last couple of months, is an update for the Webb Space Telescope. This month, it's seeing stars and taking selfies. So last month, we talked about the Webb getting out to the second Lagrangian point, or as we call it, L2. This diagram shows you the 5 Lagrangian points, and these are gravitational semi-stable points between the sun, the gravity of the sun and the Earth. And you can see that the L2 is on the far side of the sun, of Earth from the sun, so that those sun shields can always block the light of the sun, as well as the light of Earth and the moon that might interfere with infrared observations. So it's now out at L2, but it takes about 6 months at L2 in order to commission it and test it. So what are we doing for testing? Well, we're looking at stars. And this is a picture of one star, but it's one star 18 times. As you may remember, there are 18 different mirror segments on Webb. And to take this picture, they had to align the telescope so that the star was in each mirror successively. Okay, so this isn't just one picture. This is 18 pictures co-added together to show where the initial alignment of the mirrors is. And this looks like it's ratty and all over the place, but actually this is really good, because the field of view that they needed to take to ensure that they got it was about 4 or 5 times larger than this. So it's actually that these were all quite tied together. This is actually a success, okay? And then they had to identify which segments got which image. All right. And you can see that they have the segments in the A, B, and C things, and in the wings, et cetera, and they give them the numbers. Okay. Now, how did they figure out which image was from which mirror? Well, that's where the selfie cam comes in. And so this is an image from an engineering camera. We're going to give it the nickname the selfie camera, but it's really an engineering camera that looks at the secondary mirror so that they can figure out what's going on with the primary mirror. So this really is a sort of little selfie, right? Using the secondary mirror as sort of a big long selfie stick to look at the primary mirror. Now you can see one of these segments in Webb is bright. That's the one that has the star in it at this point for this observation, right? And by doing this 18 times and taking the image and seeing which mirror they've got it in to get it bright, or actually they probably figure out, get it in the mirror and then take the image, right? They can figure out which segment corresponds to which image in that mosaic. Then they can organize them according to the layout of the mirrors. This is the initial image of that star from the 18 mirrors without adjusting the mirrors one bit, okay? And you can see now this is really ratty. This is all over the place, okay? So the next thing they're going to do, they're going to align the segments, do the large scale alignments of the segments to make those stars look better, all right? And so the next step, boom, they go through and they do the large scale segment alignment to make those stars look relatively good. No, this is not perfect. This is not nowhere near finished, okay? It's just the initial large scale alignment. All right, and then they can take those 18 and pull them all together to image stack and create the point spread function. All right, so this is all 18 mirror segment images of those stars together in one, and I'm going to blow this up for you. That's what a very, very bright star looks like in the initial mirror alignment for Webb. Okay, and I'm going to bring up the Hubble point spread function as a comparison. So on the left, we've got the Hubble point spread function for a very bright star. And on the right, we've got just the initial point spread function for Webb for a bright star. And you can see how much cleaner Hubble is, but that's the goal. That's where we're headed. But the other thing is that we're so used to the Hubble, the cross-shaped point spread function. With Webb, we've got hexagonal mirrors, we've got the design. We're actually going to get a 6-pointed star for the point spread function. As well as you can see, there's a little detector bleed. I think that's detector bleed along the axis. Or maybe we're getting an 8-pointed star. I'm not quite sure. I'm learning as we go, just as you are. But you can see where Webb is now. They've got an initial bright star point spread function. And over the next couple of months, they're going to continue to do the small scale refinements to each of those individual 18 mirror segments and align them so that they get something as clean and beautiful as we see on the left in the Hubble point spread function. Our second story, ARP 143 and the giant space triangle. That almost sounds like a children's story. Let me tell you about the giant space. No, what we're really talking about is the ARP Atlas of Peculiar Galaxies. All right. Now, that word peculiar means that they've got strange shapes. And Halt and ARP created this big catalog of lots and lots of strangely shaped galaxies. This is not his atlas. This is actually a book about his atlas because they kind of make some really cool shapes and they're really quite beautiful. So Hubble has observed a bunch of these ARP galaxies, okay? And they're pairs of galaxies that have stretched each other apart. And some of them have some very fun shapes. So for example, this one, this is ARP 147. And it was, when we released it in our press package, referred to as a perfect 10. Because you can see this galaxy on the left looks like a 1, and the galaxy on the right looks like a 0. In truth, of course, these galaxies are, distorted each other in terms of their gravitational interactions. Another one, and a really classic one we released, was called the Rose. This is ARP 273. And you can see how this top galaxy here forms the rose, and the bottom galaxy here forms the stem. And this was a very beautiful thing that we released. But I got to say that we actually turned this image on its side And a whole bunch of us said, hey, you know what? This STEM galaxy actually looks kind of like a hummingbird from this perspective. So we got a lot of interesting interpretations. And one of my favorites, okay, is ARP 142. And this was nicknamed the Penguin and Egg Galaxy. And I hope you can see the idea of the penguin up here and the egg down here. I'm sure this is after somebody saw March of the Penguins and said, oh, this looks just like that. So what have we got to add to that? Well, we actually have ARP 143, and as the title of this story tells you, it's got a giant space triangle. You don't get triangles much in astronomy. You get circles, you get ovals, you get big stretched out linear things, but triangles? What's going on here? Well, you can see that this brownish galaxy over here on the left its gravity is pulling on this bluish galaxy over here. All right. And so these pair of galaxies are interacting and the gravity is pulling on this stuff. You know, galaxies are not solid objects. Okay. They are clouds of gas and dust and stars. And those clouds get pulled. And you can really see this beautiful stretching out of the blue stars here. And all the other thing that you can see is that in that gravitational interaction, it's almost assuredly that this star formation, all this blue stuff, all these newborn stars were triggered by the gravitational interaction between these two galaxies. Now, I can't prove that, but you know, that's generally a lot of what happens. When you see interacting galaxies, the gas clouds are stretched and distorted and they collapse and you do get these bursts of star formation. So this is actually what looks like to me a star bursting galaxy, because there's just been a tremendous amount of star formation recently, probably due to the interaction. And the fact that it creates this triangle is that it was probably relatively circular, but the taffy pull of the gravity pulling the stuff out makes it into this really interesting triangle shape. So that is our latest ARP galaxy for you, the Cosmic Giant Space Triangle. Our speaker tonight will be talking about Hubble from space and integral-field spectroscopy from the ground. This is Dr. Marc Sarzi, and we're very excited to have him. He is our first presenter from Europe. He is actually coming to us from Armagh in Northern Ireland. And he will be to present his talk. And it's wonderful because I was able to recruit him over the internet and be able to get international speakers to come in and talk. Marc, would you please turn on your video and start your screen share? There we go. Marc tells me that the Armagh Observatory, which is over his left shoulder, is the home of where the new general catalog, known as the NGC catalog to the cognoscenti, was actually taken and defined at Armagh. He started his career in Italy, in Padua, and did his undergraduate and some of his graduate work there. He also did some of his graduate work at the Max Planck in Heidelberg, working on supermassive black holes. He then decided to take a tour of the United Kingdom, doing work at Durham and in Oxford, and before settling down in Armagh. So we're excited to have him here. And he tells me that he is a big gamer. And no, that's not a big game hunter, or it's not an online video gamer. He's actually one of the tabletop gamer folks, and he loves the Tolkien games. So, ladies and gentlemen, Dr. Marc Sarzi.
Thank you, Frank, for the introduction. I'll share my screen now. Can you share my screen? Can you see my screen, Frank?
Yep.
All right. Let me get the beginning of my presentation and start my presentation.
Everything looks good.
Okay. So as Frank says, today I'm going to try to talk to you a bit about integral field spectroscopy, which is a very important tool that has been added to the arsenal of astronomers in the last, say, 20 years to better understand, in particular, the fuzzy and diffuse objects in the sky, which is also was also the focus of the research here in Armagh 200 years ago, almost, when indeed the NGC catalog was compiled at a time where people did not know the difference between nebulae and galaxies. That was only figured out later. And indeed, is because of integral field spectroscopy, we could really do great advances in the understanding of diffuse nebulae and galaxies and clusters. And so what I wanted to try to do today was to actually see what was the synergy of integral field spectroscopy and Hubble Space Telescope observation, since I am actually your guest tonight. So I first need to introduce you about integral field spectroscopy and spectroscopy at all. So what I'm gonna do, I'm gonna just basically give a little word about spectroscopy. So in essence, what is spectroscopy? Is basically the process of splitting light in its simple components, colors if you want, and different wavelengths. Typically, this is achieved with a prism. You may be familiar with the natural prism that are actually droplets in our atmosphere. When these droplets create a rainbow in the sky. And prism, on the other hand, is something that was more studied at the time of Newton in particular, who actually demonstrated the very nature of light. At a time, in fact, when people thought that prism, these very interesting, funny objects, were actually coloring light rather than splitting light. And Newton could demonstrate that that was actually what a prism was doing, because by putting another prism after one prism, it could actually recombine the rainbow back into white light. And nowadays, spectroscopy is a process where we try to understand the nature of particular features in the spectra of the light that comes from different sources. And that has become particularly possible after we had ways to actually record the spectra that we are observing, i.e. with the advent of photography. So what you can see here, for instance, is the first picture, not even a picture, this is actually a daguerreotype, a prototype of a photographic plate. And this is actually a spectrum of the sun that was taken by John Draper in 1842. And when we come to the sun and the first observation of features, well, this is a prime example, because spectroscopy is, as I said, used to understand study the features in the spectra of different objects and try to use this feature to actually infer how the light is produced from, in our case, astrophysical objects such as stars and gas. And so this has led in particular to the discovery of different elements early on in the 19th century, for instance, the discovery of helium in the chromosphere of the sun. This was something that was done after a particular solar eclipse by Jules Jassin, who noticed that there was a lot of emission coming from the corona of the sun, and had the idea of later taking a spectrum. And this was also done by Norman Locker basically at the same time. And this led to discover a particular line that was not known at the time, which turned out to be an entirely new element that is otherwise very rare on Earth, which is helium. So nowadays we don't use prism to create a spectrum. We use what is called a diffracting grating, which is a series of reflecting surface inclined, and the light that comes on this diffraction rating, because of diffraction and interference at the end, is deflected at different angles depending on their wavelengths, and we can then collect this with a detector and actually observe a spectrum. Why do we use gratings instead of prism? Is because we can actually really be very careful in the construction of these inclined surfaces, and really go down to very high precision in manufacturing, so having a great control on the outcoming spectrum that we get. One particular kind of grating that you may be familiar yourself are your old CDs. These you may have noticed that when you incline them, you actually get a little rainbow out of this. That's exactly the process I'm talking about. And in fact, there are ways where you can actually build your own little spectrograph, as shown in this picture, that you can use to point it to different sources such as the sun itself, or maybe a light on incandescent lamps, or from a neon light, and then observe the difference of what you get from those kind of spectra. Sometimes grating is also combined with a grism. Okay, this is an example of what we call a grism then. This allows for the construction of more effective and compact instruments, because we don't have to place the camera for imaging outside in a different direction, where we have also on the other end the light from the grating coming from a different direction. But we can basically have the light going straight away through the instrument, put the camera at the end, and then just insert the grism if we want to actually have a spectrum or not. But anyway, this is a bit of technicalities. I just wanted to actually give you a little insight on how this instrument works. But what do we actually look up in the sky when we actually take a spectrum? And what do we learn? Where does this light come mostly from? Well, it mostly comes from stars and gas in the sky. So when you see stars, these produce mostly a diffuse continuum spectrum, which is the brighter and the bluer, the more hotter is a star. And then this light from star often is absorbed by interstellar gas and is then re-emitted at very specific frequency, creating what is actually called an emission spectrum. Let me just try to actually put my laser pointer here so you can see this. So that's what I'm talking about here. So this is the emission spectrum of an excited cloud of gas. As it cools down, it emits radiation at very specific frequency, and the very excitement actually takes place in the form of light from the stars being absorbed at very specific frequency in turn. Just like it is emitted at very specific frequency, it is also absorbed at very specific frequency. And when this gas actually is on the surface of a star, so when we're actually talking about the atmosphere of a star, then it produces a set of absorption features that indeed we observe in stellar spectra. So a stellar spectrum is never a continuum. It is in fact a superposition of a stellar continuum and an absorption spectrum from the gas in its atmosphere. So that's what I'm talking about. And this is very important because different stars have different kind of spectra. So there are stars that are very blue, and they're typically young and very bright. And then there are stars that are very red, that are typically old. However, it is the distribution of these absorption lines that actually tells us something more about the stars. It tells about not only about the temperature, but it also tells about the surface gravity. And also because these absorption lines come from specific elements, it does also inform us on the kind of element abundance on the stars. Ultimately, this gives us a hint on the age and evolutionary status of a star. So, because what you can have is that you can have red stars in the sky that are actually either normal, average, small stars and very bright giant stars. And it's through the spectra that we can tell the difference. And this was very important to actually crack the riddle of why there are in the sky different stars with different colors and different brightness. So the other source of emission that we can have, as I said, are emission line from clouds of gas that is excited. A typical example that we can see is the Orion Nebula, which is actually gas excited by bright young stars that have been forming at the very core of this gas cloud. And in the case of a stellar spectrum, the feature that we actually are interested are the emission lines. And the relative intensity of these emission lines can tell us about, again, the element abundance, but also the source of excitation, which, to put it simply, in the case of this Orion Nebula, it is the young stars, but it could be also, in the case of a planetary nebula, a central, much hotter single stars, or in the case of a supernova remnant, it could be the shocks that the gas actually goes through as it expands in the stellar medium. Now, how do we go from the single stellar spectra that we see in our galaxy and the single gas clouds spectra that we see also nearby to understand the spectra that we obtain from galaxies? Now, what we need to keep in mind is that because galaxies are so far away, effectively, what we see is mostly emission from very red giant stars, from very blue bright stars, and from diffuse gas from star forming regions. So this is what gives actually the appearance in galaxies of maybe the red central regions dominated by old giants, the blue spiral arms where you only have these these very bright young stars. Necessarily, they have to be here where you form stars because these red giant stars, these blue stars actually don't live long life. So if you don't keep forming them, they will soon disappear and then the galaxy will simply turn red. And then these red clouds of emission lines, they become even more apparent if you actually look at specific frequencies and take what we call narrowband images of galaxies. And so overall, when you take, imagine taking the spectra of a single galaxy, like, if you could just take the spectrum of a galaxy to a single fiber, for instance, then you're basically confronted with two typical kind of galaxy spectra. So on the left, and in blue here, what you see is the spectrum of a galaxy where you have active star formation. So overall, the stellar continuum looks blue because it receives a lot of contribution from the blue bright stars that are continuously forming in the star forming region. And of course, you also have, like from the Orion Nebula, a lot of these emission lines from the very regions where the stars are forming. Conversely, in a galaxy where there is no longer star formation, what you have is a spectrum that is dominated by red stars, and therefore the total stellar spectrum of a galaxy look essentially red, and you don't see any ongoing star formation, therefore you don't see any prominent emission lines. Of course, life is a bit more complicated than this. Sometimes you have emission lines that come from gas in the immediate vicinity of an accreting black hole. This will give you a completely different kind of emission lines, but I can talk about this maybe in the questions later. So what can we learn from this kind of spectra? Well, we can try to decipher the composition of stars that actually enters in the final total spectrum. Or if you want, we can try to find out the mix of old and young stars that are ending up giving you the total spectrum of a galaxy. And we can also infer the total amount of gas that is being excited by newly formed stars. These two aspects in turn can tell us something about the star formation history. So if there are a lot of young stars, very few young stars, then it means that we are actually forming stars. Whereas in galaxies like this, you will find that the star formation history basically was quenched a long time ago, and there hasn't been any new star or even intermediate age star for some time. And then the emission lines that tell you actually how many stars are presently forming, so the present rate of star formation. And of course, this kind of exercise can be done both for nearby galaxies and for further away galaxies. Another thing that we can do, which I'm sure you're familiar with spectra, is to use the Doppler effect to essentially measure the velocity of the stars and of the gas. What we do is that, for instance, if we have a galaxy that is rotating, what we can observe is that the gas and the stars on this side of the galaxy, imagine that the galaxy is, rotating this way as you see, then the stars and the gas in this side of the galaxy will be receding from us. Therefore, the emission line from the gas and the absorption lines from the stars will be redshifted. And the amount of redshift that I will measure can be translated directly into a velocity. And likewise, on the blue side, on the approaching side, I will actually be measuring a blue shift, and therefore a negative velocity towards me. This is, of course, once we take out the overall redshift of the galaxy, because this is due to the expansion of the universe. So the galaxy is actually moving overall away from us most of the times, except for the most close galaxies that actually, like Andromeda, is falling onto us. So let's now go back to spectroscopy, and let's try to understand how this is done in telescopes. The simplest thing that you can do is that you can simply take your grism or your grating and put it in, across the optical path, and simply transform what you see, an image, into a set of spectra. HST has such kind of technique, which is called slitless spectroscopy. And in this case, what you can see is, images of distant galaxies for which you immediately get some short spectra here. This is very useful and very efficient because you get lots of spectra at the same time. And it's very good when you have discrete sources and distinct sources like this. But for a galaxy, that won't work, because what you have is that you have continuous sources, one next to each other. Okay, and even here you can see that these three galaxies, for instance, it is hard to actually, their spectra actually superimpose to each other. So imagine this for a diffuse source of light, such as, a galaxy where the light comes from every place. So in this case, what you can do is that you have to make a hard choice and decide that you want to only look at one part of the galaxy, like in a long slit, in this case, in only one direction, and essentially just take the spectrum of this region, of this region, of this region, of this region, and take this region and disperse them along the wavelength direction when you put them through your spectrograph. So what you're seeing here is a typical long slit spectrum of a galaxy, where you see a very bright continuum coming from the central region of a galaxy, which is very bright. And then you see also some absorption lines here, and you can see also some emission line here from the gas. Now, this is needed, as I said, to avoid overlapping, but it's not particularly efficient. If I really want to cover and understand the galaxy property, well, I also need at least to put something along the minor axis, or maybe at an intermediate angle. And every time I do this, I have to expose again at my telescope, and it takes a lot of time to essentially, through this method, to cover the entire galaxy. True, galaxies are also axisymmetric. They have a symmetry. So in the end of the day, I could say that, if I have a disk, what I observe here should also be observed here and here and here and here. But not all galaxies are axisymmetric. And also there is another important thing to keep in mind, aspect to keep in mind, is that as I move into the fainter region of a galaxy, I collect less and less light. Ideally, what I would like is to be able to have a bigger slit here and add everything together. And this is precisely what is actually possible when, instead of going only in one possible direction, you can actually take a spectrum everywhere in your field of view. So this is where integral field spectroscopy comes in play. There are various ways to do this. Early concept actually used what is called lenslets. So the idea here is that you have to have the focal plane. At the focal plane, you have to split your galaxy image. You have the light coming from the galaxy that is focused on the focal plane. And at that point, you actually have to find ways to split the light from of the galaxy. So you can have little lenslets that focus these regions in little regions here, just before you go to your spectrograph. And then you obtain various little spectra here. That's one concept. Another concept is that you attach a fiber, an optical fiber, in each of the section of your focal plane, and then you carry the fiber and you align them along the direction of where you typically have a slit, and then you pass this through the spectrograph, and again you have a series of long slit spectra. Or you can have an image slicer where you take this image and you send it here, this image and you send it here and here, and then again it's a longer slit. Either way, what you, at the end you end up is with a spectrum everywhere in your field of view. Of course, it's not everywhere, and there is a finite resolution that comes out of this process, and you end up with what is actually called a data cube. The data cube, actually, you can see it in two different ways. You can see it as a spectrum at every place in the galaxy. So for instance, this is actually a spectrum that is in this place, then a spectrum from the center, a spectrum from here. So you can extract a spectrum at every location of the galaxy, which of course, or a nebula. I'm just talking about any diffuse object here, which is very useful because you can learn about all these kind of properties about the stellar content or the amount of gas that is being excited by stars everywhere in the galaxy. Or you can look at this as a series of monochromatic images. So at every place, as you travel through the cube, you can actually see an image. The image will be slightly different at every wavelength, depending on what is happening to the spectra. So at some point, you may actually have very strong emission lines coming up, and you will be able to see this in the image. So when it comes to multifold field spectrograph, the most powerful IFU that we have at the moment is the so-called MUSE spectrograph. This is based on the Very Large Telescope at the European Southern Observatory in Chile. And what actually is seen in this animation is the Orion Nebula that I showed you before. So let me just remove my pointer here, because I actually wanted to start this other movie, and I can talk about them at the same time. So what you see is that is a particular galaxy. This is what we call a polar ring galaxy, where there is a main body that is basically a disk, and then there is a polar ring of gas that has been acquired, gas and stars that have been acquired in a second time. And so as we move through the cube, you can see different images. And now you will see, for instance, the image that comes in a very particular moment when we pass through a particular place where you have a very strong emission line from hydrogen. And then you will see first emission from one side of the galaxy, and then the emission from the other side of the galaxy, because that's where the lines are according to their redshift because of their velocity inside the galaxy. And here was the Orion Nebula, where on the other end, this movie was actually showing you the idea of having monochromatic images. And again, here is showing you images in the blue, in the green, in the red, and also at this very particular special wavelengths I was talking about, where you have a lot of emission. So I want mostly to talk about integral field spectroscopy and apply to galaxies. I have to make a choice here. And so I need to give you a very short introduction. There are very nice, very short introduction that you can find on the web and booklets. And these are some of my favorites. And so what about galaxies? What is the riddle of galaxies? What do we see about galaxies? Why are these so important? Well, they are the building block of the universe as we know it, where most of the baryons are. And they come in different shapes and colors. They're not simple objects. Some are disky, some are rounder, some are red, some are bluer. They also come in wide range of mass and sizes. So for instance, this is an image of the Fornax cluster, which is a big galaxy cluster in the south, in the constellation of Fornax. And you may not see all the galaxies in this image, but these are actually all little galaxies. So there are many galaxies that are very small and a few galaxies that are very big. So this is what we call the mass function of galaxies. So different colors, different shapes, wide range of mass and sizes. And finally, how do they go then to this present size and shape and color distribution? What are the processes? So essentially, we can think in a nutshell of galaxies as growing through two main processes. One is star formation, where you accrete over time gas from the intergalactic medium. This gas cools down in the plane, equatorial plane of a galaxy, and forms stars in the process. When it forms stars, this will lead to the formation of a stellar disk, and it will have bluer colors because, as I said before, the light will be dominated by the blue stars, which are the young ones, and they are very bright. Another way to actually grow galaxies is to simply merge them together. Frank just showed a lot of pictures of merging galaxies before. These are beautiful features, and they actually show that galaxies can merge together. In the nearby universe, actually, these processes are quite rare. They are not that frequent, but when they happen, a galaxy can, in the end, just double its size in one go if we count as a galaxies of similar size, as it would be the case in the future between our own galaxies and the Andromeda galaxy that you see on the left. When you actually have these big mergers, you also have a lot of star formation that is triggered as the gas is funneled towards the central regions and accumulates there, and it gets compressed, and therefore cooling happens more easily. And what actually happens in the process is that you may start with two disk galaxies, but as the stars get reassembled and fly by each other, in the end you may end up with a rounded galaxies, like an elliptical galaxy. Some galaxies, however, have stopped forming stars long ago. And this is the other end of the process. You can grow stars, you can grow galaxies by merging together, but then sometimes stars stop forming. And there must be some star forming quenching mechanism, and we know of some of them. So what we see on the left is star formation that is quenched by star formation itself, in a sense. What you have is that as stars form furiously in the center of a galaxy, then through their radiation and supernova explosion, they may actually funnel away the gas from the central regions and perpendicularly out of the galaxy. Sometimes this gas goes in the very center, where we now know there are many supermassive black holes. When these black holes start to accrete gas, they actually become active, in the sense that their outer region, they're outside the black hole. What you have is that you form an accretion disk that becomes very hot, radiates a lot of light, and also you form a jet of high energy particles. Both these kind of very energetic processes can drive gas out of a galaxy, or they can actually heat up the gas around the galaxies. And either way, you don't have any more gas, or you have gas that is heated up and not cooling down to form new stars. And then you also have environmental processes where galaxies join galaxy group or clusters and get stripped of their gas in the process, or through interaction with other galaxies also see their gas material being lost. And of course, this is actually a very important process, because we know that galaxies, live also in different kind of environments. There are galaxies in group, in clusters, and also in the field. And whether you are in a group, in a cluster, or in a field also affects your chances of meeting other galaxies, or to effectively merge with other galaxies. And in turn, this, limits your chances of growing by mergers. So in a nutshell, these are many of the processes that we know are regulating the growth of stars and galaxies. But we need to get this picture right also across time. And so what we have here is a graph that shows you how the star formation, and this is shown by these crosses here, or the black hole accretion, basically how fast black holes were actually growing over time. And so in the nearby universe, we can see, say, this present rate of star formation. But when we go back at redshift 1 or 2, so redshift 1 is roughly half of the age of the present universe, redshift 2 is something like 3 giga-years after the Big Bang. This is the epoch where galaxies were forming stars a lot more intensely than now. And likewise, also their black holes were forming, were growing actually, and accreting a lot of more of this gas and growing accordingly. So we also need to get this picture right. There are two processes in which we can understand galaxy formation. One is to look at galaxies nearby in greater detail. And the best example is actually to look at, the stars and gas in our Milky Way, although unfortunately we are limited in where we actually can study these objects directly in our neighborhood, or basically mostly on our half of the galaxy. Or we can look back in time and look closer at galaxies when they, look far back in time, but with less detail. So integral field spectroscopy can actually help in both approaches, as also, of course, Hubble can do that. So let me just give you a little two examples of how integral field spectroscopy can tackle on these processes that I mentioned before in terms of growing stars. This is not necessarily linked to the role with Hubble. I just want to give you a little use these two examples to actually show you actually how integral field spectroscopy works. So what you have on the left here is an Hubble Space Telescope images of a beautiful galaxy, which is called NGC 7742, which has a bright core of what we call a bulge of yellow stars, and then is surrounded by a ring of blue bright stars. So where we actually see a lot of star formation. This is the same image of an image for the same galaxy with the Muse integral field spectrograph. And what you see here is what we call a reconstructed image. That is, at every place in the field of view, all we have done is simply add up all the light in the spectrum and essentially attain what we call a white light image. So you can see that the two images correspond very well. The spatial resolution is clearly worse for the Muse data because they're from the ground, but they are, still, you can tell a lot of details here. What you're now seeing here is, on the other hand, two particular measurements. On one, in the middle, what I'm showing you is the stellar velocity field, and on the right, the gas velocity field. So what we have done is that we have taken the spectra at every place in the galaxy. Sometime, in order to gain signal to noise, what we have done is that we have binned up the spectra and added them all up in these particular regions that are a bit irregular, which we call bins here, to get good spectrum. And what we have obtained here is simply we have measured the redshift or blue shift of the absorption line in the stellar spectra with respect to the expected position at rest frame, and therefore inferred the velocity of the stars in this side of the galaxy as opposed to this one. In red, I'm showing you stars that are receding from us, and in blue, I'm showing you stars that are approaching us. So overall, you can think of this galaxy moving in this way. What you see on the right, on the other end, is the same exercise, but when I actually focus in the spectra at the emission line from the gas. In this case, you can see that the approaching side actually is where on the other side of the galaxy. So this means that this gas is actually moving in this way, right? So what we are actually seeing here is gas that is moving in the opposite direction of the stars in this galaxy, which can only be interpreted as if this gas was actually accreted as the result of a merger of the galaxy, a small galaxy, maybe a gas-rich galaxy, that has now been completely destroyed, but this gas is left and has settled in the plane of this galaxy, and is actually rotating in the opposite direction of the stars. In other words, this is also cannot be interpreted as gas that was, internal in the galaxy, as one would expect from stellar evolution, because stars, we know they explode and release their gas in the interstellar medium. So if this gas was of internal origin, it will basically rotate in the same direction. So what we are seeing here is direct evidence with integral field spectroscopy of a beautiful past merger in this galaxy, is the remnants of this merger. This is this was also possible with long slit spectroscopy, but here we can really have and appreciate things in greater detail and work out more precise numbers. I also mentioned the star formation history of a galaxy that we can try to recover by understanding the different mix of different stars of different ages in a galaxy, and how this could be also linked to the star formation process that actually led to the growth of a galaxy over the past. So if we look in a galaxy nearby and we reconstruct the star formation history, we can actually understand how this galaxy formed its stars in the past. So what you see is this nearby galaxy that is quite big in the sky. It's called NGC 3115, and each of these squares is actually a Muse field of view, which is basically one Archimedes square. And so what you see here, long story short, is 6 panels, and in each of these 6 panels, what you see is the amount of stars that at any given age. So for instance, when you look at stars that are between 0 and 4 billion years old, we can call these, young stars, so to speak, you can see that they're all in the disk. So these are basically stars that formed quite some time ago, but they formed from gas that settled in the disk. And the story is more or less the same until you go at 10 gigayears ago. It's only when you go for stars that form, just a few billion years, 1 or 2 billion years after the Big Bang, that you see stars that actually are distributed in the so-called bulge and more spherical distribution. So this is consistent with the idea that, in galaxies, they form violently in the past. And this led to formation of stars and distribution of stars in a more spherical and, fatter regions, which we call bulge. And only later, there was a lot of star formation more relaxed in the disk. This is for this particular galaxy. Okay, so now let's come to talk about Hubble and integral-field spectroscopy. And I wanted to actually give you 3 examples I actually ended up choosing of fruitful interaction of Hubble measurements and integral-field spectroscopic measurements from the ground, where this could be very complementary. So my first choice is about globular clusters, which I haven't talked about yet. But globular clusters are very important because they tell us about the assembly history of galaxies. So that those processes such as mergers. And in particular, they tell us about the assembly of the outskirts of galaxies, those faint, diffuse, extended regions that we see in galaxies, in particular in very big galaxies, such as the one you see on the right, which is called M87, which is the central most bright galaxies in the Virgo cluster, which is also incidentally the galaxy where we have actually imaged the donut, the accretion disk around the center black hole of this galaxy. And so all these little dots that you see here are not stars in our galaxy. These are actually globular cluster in M87, things that in our own Milky Way will look as beautiful as this cluster here. So in our Milky Way, we could actually resolve all the stars in this, especially with Hubble, all the stars, or basically a great number of stars in this cluster, but we can't do that at far away. And in fact, what we need is Hubble Space Telescope observation, even just to identify these clusters in these distant galaxies. So why are these globular clusters important? Why do they tell us something about the story of the assembly story of galaxies? Well, it turns out that globular cluster comes in 2 kinds of flavors. They're all made of old stars, and yet some are bluer than others. So they come, if you want, into a red and blue flavor. Now, normally, as I mentioned before, a blue star would be a young star. So a cluster of blue stars like a Pleiades is a cluster of young stars. But that's not the case for globular clusters. So in the case of globular clusters, what the color is actually telling us is a more subtle effect, which is telling us about the metal abundance. So when a cluster is actually poor in metals, it appears bluer. When it's redder on the other hand, it means that it is more abundant in metals. And in turns, this tells us something on where this globular cluster may have formed. If they are rich in metals, it means that they have formed in more massive galaxies originally. Okay, those galaxies may not be longer, may no longer be around. This is where those clusters may have formed, or they may not be around in the way we know them now. Why is that? It's because when you have galaxy and you have stars forming in it, and you have stars exploding in it and releasing their gas in the interstellar medium, those stars then this gas then reform into new stars, and then the process continues. And every time, what you have at the center of stars is that you produce more and more metals. And so as the story goes on, as long as you can retain the gas in a galaxy, the interstellar medium gets more and more enriched in metals, and that gets imprinted in the stars that form in that galaxy. And the same applies then if that particular globular cluster formed from a very metal-rich interstellar medium of a massive galaxy. In a dwarf galaxy, then basically the feedback process I mentioned before, in particular star formation, are very efficient because they can drive out very quickly the gas out of a galaxy, because the galaxy is too small to gravitationally retain its metals, its gas. And so in that case, the clusters formed from a very metal poor environment. And so they are bluer. And this connects indeed to the idea that in galaxy formation, you may have a two-phase process where you have an in situ formation of where stars form in the same place, essentially, okay, in a galaxy over time. And then there is metal enrichment going on and the formation of red globular cluster. And you have the accretion process, in particular for metal poor dwarf galaxies. Okay, and these two processes, the relics of these two processes, may still be imprinted in the halos of galaxies. And we can trace this in particular from the globular cluster population. What was more important, red or blue formation? It turns out that in most globular clusters, in most galaxies, what we see is a distribution of blue and red clusters that appears to be double peaked, as if there are indeed two distinct populations. So that means that the two processes were indeed present and important. And this is something that can only be done in external galaxies with Hubble, as I said. Hubble is key to recognize this globular cluster, which have the typical size of maybe 10 parsecs. So they are very, very small, at most 10 parsecs. They're very, very small, subarc second. So you really need Hubble to see these clusters. And you also have immediately for free, if you observe these clusters, these images in two filters, you can determine their color. And this is what exactly has been done in the ACS wide field camera surveys of the Virgo cluster, for instance. But this work by Peter Jordan in 2015. But this is the story as far as only colors are concerned. What if we could measure directly the metallicity of these globular clusters? To do this, we will actually need spectra, okay? And this is what is possible with integral-field spectroscopy and with MUSE. So this is work that Katja Fairon did a couple of years ago. So what we did there is simply to take MUSE data of galaxies for which Hubble had already identified a lot of globular clusters and extracted spectra where possible around the location of this globular cluster as indicated by Hubble. So that's the key role of Hubble, is basically to tell us where the cluster were. And the spectra that you see here on the right, sometimes they're good, sometimes they're not that good in terms of quality, but we can still, fit them with models where, the abundance of metals or the age of the clusters can be changed. And essentially you work out what is the best age and what is the best metal content, or what we call metallicity. And in the end, estimate directly the metallicity of these clusters. And it turned out that the relation between the metallicity of the clusters and the color of the cluster is not a one-to-one relation. It's not even a linear relation. It's a more complicated relation. It's what we call a non-linear relation that essentially tells you that you cannot simply translate one from the other. You cannot just go from color to metal content straight away. There will be a change when you do that. And in fact, this is the case of one particular galaxy, the galaxy I showed you before. This is the distribution of colors, and the metal content distribution is completely different. And in general, when you do this translation, things get more complicated. And so that's an example that may not be super exciting in the sense that it doesn't lead to a clear result, but it's very important because it tells you that colors are not all, and you need spectra. And integral field spectroscopy will be very important to, finally crack this puzzle in the future. On another example, let me talk about supermassive black holes. So thanks to Hubble Space Telescope in particular, we now know that there are supermassive black holes nearly at the center of every galaxy that we looked at. We know that there is a tight relation between the mass of the black hole and the mass of the galaxy. Big black holes live in big galaxies, small black holes in small galaxies. It's a very important relation because it hints at the fact that galaxies and black hole evolved together. And in fact, we see in the plot I showed you before, when we look back in time, we see that black hole grew in a parallel way as stars forming galaxies. You need very high resolution to really measure the mass of a black hole, and that was very important that we had Hubble for that. And more mass measurement are needed to really understand the link between black holes and galaxies. As I said, Hubble played a big part, and so here's an example of how you can measure the mass of a black hole. In the case of Hubble, we only have a long slit spectroscopy on Hubble. We also have slitless spectroscopy, as I said before. This instrument in particular is called STIS. So what you see here is the slit of STIS, and then you can see here how in particular, this is the position in a spectrum, or if you want, is the velocity of a particular emission line. So this is tracing the motion of the gas near the center of the galaxy. And as we come from outer part towards the nearer part, what we see is that the gas velocity suddenly increases. So here you have a very strong blue shift, and here we have a very strong red shift. And then the signal gets mixed in the center where we don't have enough resolution. But what this is showing you is the typical trend that reminds you of the Keplerian curve of planets around the sun. So what you see is that the gas clouds in this galaxy are behaving just like the planets around the sun. So they are moving faster and faster as they get closer to something that is very massive, and everything, and all this mass is in the center. And if you do the math, you actually work out that this actually to be a very concentrated dark object with a very big mass of a few times 10 to the 7, 10 to the 8, if I remember correctly, solar masses. Now, this was an example of when you have a very nice and well-behaved gas kinematics. And in this case, you can just use the Hubble Space Telescope observation because all you need to know is how the gas moves nearby. Well-behaved gas, on the other hand, is very rare in galaxies. What we are not short of is stars. But these actually move in very complicated ways, which require careful modeling. And furthermore, you have stars that spend both time close and far away from the center. So if you really want to understand the galaxy, the entire dynamics, and how this is affected, by the central black hole, overall, you need, in fact, to map the entire kinematics of the galaxy, or at least in the very central region, very carefully, and have some constraint on how stars still move in the outer region. So you need integral field spectroscopy also here. One of the first examples where we could combine integral field spectroscopy in the outer part and Hubble Space Telescope spectroscopy in the center was in the observation of and the black hole mass measurement of this tiny little galaxy that is called M32. It is actually a very important galaxy because the black hole in this galaxy is very small, and it was found to be very small in a very small galaxy. So it is a very important galaxy in the relation between black hole mass and galaxy mass, because the extremes in a correlation are very important to really determine the correct slope of a correlation. So this combined Hubble Space Telescope images and data with an integral field spectroscopic data measurement from actually a spectrograph which was called SORON. It's a very complicated acronym, but it was simply justified because people in that team really like Tolkien, like me. And what you see here is basically Sauron looking through his orb of a stolen Palantir at the kinematics of this galaxy. And so here's what we can find. Here we have the this long slit kinematics. What you see here is the velocity curve of a galaxy. And what you see is also the velocity dispersion, how random is the motion of the stars as you move from the outer part of the nucleus towards the very center. And things get very messy and very fast near the center because stars do not want to fall into the black hole, or put another way, only the stars that move very fast have not fallen yet into the black hole. And these very central measurements were combined with integral field data for the kinematic at larger radii. And these are the data. These are the data. And the line here is the model. And this actually beautiful map is actually the model for this velocity and velocity dispersion field. And this is work that was done 20 years ago now, gosh, by Alan Verolm, and was one of the first, if not the first, combination of integral field spectroscopy and Hubble Space Telescope spectroscopy. Since then, actually, interestingly, this exercise has not been repeated very much because of the advent of adaptive optical observations. These are observations that you can do from the ground, where you can correct for the blurring of the atmosphere and basically get similar, or not that, of similar quality, not quite as good as Hubble spectroscopic measurements or even images. So for instance, here's an example of how this was done for measuring the motion of the very central stars of our Milky Way close to the center. And this is an example of how the adaptive optic works. It makes stars sharper, and the image is sharper, and you actually can see more stars in the process. And when you follow the motion of the stars over the years, you actually infer the presence of something big in the center that is pulling the stars around. And this is what led also to the Nobel Prize of Andrea Ghez and Rainer Genzel. So even when you have these adaptive optic observations, Hubble is still very important, because Hubble is needed to give you the best possible images, and you use these images to infer, in turn, what is the stellar distribution, and the stellar mass all the way to the center, where you actually want to do a fine balance of actually telling what is the relative contribution to the gravitational potential of your putative central black hole and of the stars. So you want to be able to really know what is the contribution to the gravitational potential of the stars only. This is why you need HST images, because the ground-based adaptive optic observation do not give you actually quite as good the spatial resolution of Hubble. But what is also very important with Hubble is that because you can use these images to actually understand what is the quality of your adaptive optic correction. Frank also mentioned this for me, thank you very much, when he talked about the PSF. The PSF stands for point spread function. So this tells you how much the light from the point source is distributed out in space. And this is also important because we actually need to know exactly this detail when we build our model for the motion of the stars and the gas. in this case, just the stars. And we convolve these models with this point product function to actually make good prediction for the observed stellar kinematics. But to know exactly what is the point spread function, we can use a point source as a reference, or when we don't have this, or if we want to actually monitor the point spread function near the center of a galaxy, we can actually use as a reference the Hubble image and convolve this maybe with a dumb shell, with a PSF model until we actually have a perfect match to our low resolution Muse images. So Hubble Space Telescope is, and high resolution images from future space telescope will still be key to the modeling of the central region of a galaxy and determination of black holes. I want to conclude now with a couple of words on distant galaxies. So Hubble was pivotal in imaging galaxies in the distant universe with surveys like the Hubble Ultra Deep Field. We know that, and I mentioned this before as well. However, if you this gives us a lot of detailed images of galaxies incredibly far away, but we don't have great spectra. We don't actually get a spectra for these galaxies, so we don't really have spectral properties, and we can only infer some of the estimate star formation rates in these galaxies. And in terms of redshift, we actually have to follow this up with spectroscopy observation to really know at the velocity at which they're moving and then infer their distances. So the best way to do this is using integral field spectroscopy. So you just take place your integral field spectrograph here and you get spectra everywhere in the field. So we just have to wait another 10 years after the Hubble test field, and finally Muse came online. Sorry, this wrong Muse. This actually is what you get here. So this was the Hubble Deep Field again, and on the left you have the reconstructed image of the Muse field of view. And in each of these points, we get a spectrum if the conditions are right. Not always we get a spectrum. And so this is the distribution of the spectra that we got. And interestingly, quite amazing is that with just 100 hours of observation, we get something like 1300 redshift here. This was 10 times more than all the redshift that were obtained in the previous 10 years since the Hubble Space Telescope observed this particular field. Again, the Hubble Space Telescope was not just a particular addition here, it was key because in extracting the sources here, we used as priors the precise location of where the Hubble Space Telescope images tell us where the galaxies were. But sometimes we can also find objects that were not identified by the Hubble images because in particular they had properties that were not captured by the broadband filters of the Hubble images. At the very close end of this Hubble Deep Field, say between redshift 0 and 1, so almost up to half the age of the universe, these Muse observation also delivered proper maps for the velocity of the stars and the gas. So what you see here is the Muse white light images of these very distant galaxies, the HST image, and then here you have the velocity and velocity field of the stars. And using the HST images, you can construct dynamical models to actually interpret the velocity fields. And the result actually is that by the time that we reach around 4 to 7 giga-years ago, it seems that regular settled disks were already in place in the universe, which is kind of interesting, if not amazing, if you think about it. But that was not the case, and this is leading now to my conclusions for very distant galaxies. So when we jump to redshift 1 to redshift 2, well, you see that even, and we do this in first place, this was done by Natasha Forscher-Schreiber in 2009 using a Symphony near-infrared spectrograph, always at the VLT. Here also you find that even when they are regularly rotating, galaxies have very turbulent disks. So we are looking at star-forming galaxies, but it's not clear, what they look like. And even when they are regularly rotating, they really have disks that are clumpy and they have really strong turbulence in them. So they're not quite like the disks that we observe today, or even that we observe, by 4 to 7 giga-years ago. So here we're talking 3 giga-years after the Big Bang. And so lastly, to really assess whether these were disks or not, a more recent study that used HST is the one by Sergio Tacchella. I want to mention just because it's the last connection between Hubble and integral field spectroscopy in these very distant galaxies. As an example, here you have the images from Hubble. They are not super great images, but that's the best that we can get. And still the analysis here of how the light was distributed as a function from the center tells us that these galaxies, they really are disks for the most part. But they are not like the disks today. This brings us to the conclusion that, especially if we want to explore galaxies in this regime, we now need JWST. Unfortunately, JWST finally has an integral field spectrograph. So we are past this regime where we had to use Hubble for great detail imaging and ground-based integral field spectrograph on the ground to really get spectra everywhere and understand and combine the two. Now, JWST has an integral field spectrograph, so it can do these kind of things. Admittedly, the field of view is very small, but then again, very far away galaxies are also very tiny. So, and here I will basically stop. Thank you very much.
All right. Thank you very much, Marc. That was incredible amount of information, not only just about getting into the basic spectra and long slit spectroscopy and then working to integral field spectroscopy, but then all these various uses of IFS across the gamut of astronomy. So one of the things I wanted to ask to make clear for our audience is the pixel resolution. Okay, so when we take an image with Hubble, we're used to having tens of millions of pixels, right? We got a 4K detector, so 16 million pixels per image, right? And Muse, if we think of that as the standard, which is sort of the definitely the high class of IFS. What is its pixel array? And then somebody asked online, which is a really cool question, was what is its wavelength spacing as well? How many nanometers between different pixels in the spectra, if you want to think of it. So you've got this data cube, and you got images, and then you got the images stretched out over wavelength. What's our resolution of this data cube?
Okay, so yeah, thanks for the question, because this is the kind of data that I didn't want to delve into. But so, as you say, we are talking about 1/10 of an arc second for Hubble, okay, which brings you to, say, 10 parsec at 20 megaparsec. So the nearby clusters of galaxies with Hubble, you can resolve 10 parsecs if you want. With Muse, we actually have a good sampling of 0.2 arc second per pixel, which in the case of integral spectroscopy is called spaxels, because it looks like a pixel, but in reality it does have a spectrum all the way through. But this is just done on purpose so we can sample very well the PSF. In reality, we are limited by ground-based seeing, so sometimes if we are lucky, we go less than an arc second. So especially at VLT on Paranal, you typically have 0.8 arc second of resolution. So it's still a good 10 times less than Hubble. And then in terms of wavelength range, it goes from 4,000 to 9,000 essentially. Well, 4,500 to a bit more than 9,000, which allows you to essentially cover typical optical spectrum where you have the metal lines, where you have the Balmer lines for recombination lines from star forming region. You can cover also oxygen-free and other very strong forbidden lines from other kind of excitation such as black hole accretion. And then in the far, well, on the red end, you have the calcium triplet, which is very important. It's a very strong absorption line. And yeah, that's a good range also to also touch on another aspect that I didn't touch, which is the reddening. So with spectroscopy, we can talk about gas and stars, but we can also talk about dust that absorb the light more efficiently than blue and the red. So we can actually appreciate how much a galaxy spectrum is reddened or not by dust.
Okay, so I guess but one point of the viewer's question was, how many of these layers in spectra do you have? Between 4,000 and 9,000, is there, is it every 10 nanometers or 20 nanometers or what?
It goes every 1.2 angstrom, which is a tenth. But essentially, you have 3,600 individual images.
That's the number I think they were looking for, 3,600 layers. So you're taking 3,600 images basically with every observation you do with Muse here.
Yeah.
That's cool, isn't that? I just thought that's a lot of fun. All right, so we've had a good chat here on the YouTube, and Grant Justice has been monitoring it a little bit more closely than I have. So Grant, would you like to turn on your video and bring up some of the questions you saw in the chat?
Absolutely. All right. So first up, you got my first question. I was going to ask it too. I loved that one. That's a really good one. Secondly, kind of continuing on with our theme of like Muse, and for anyone that needs a reminder of that, it's multi-unit spectroscopic explorer. I get lost in the acronyms as well. But what would be the difference between a Muse ground-based versus a Muse like low orbit versus a Muse? In his question, he was saying something on, like, for instance, the moon, something that would be outside of the normal range of interference, but maybe half of the year wouldn't be functional. How would that affect your data, your observations, if you had something further out?
For sure, if we were on the moon, that's a good interesting. Let's talk about. Give me the moon, okay? So
the online loves
the moon is all yours, okay?
Okay, the moon is mine. So various things. First, I don't have an atmosphere to deal with. It's true that Muse also works with adaptive optics, so we can do the same trick. In fact, we can make the resolution better, but it still goes from, let's say, 0.8, which is the best natural seeing, to perhaps 0.4, 0.3. So it's like correction for super duper natural imaging rather than bringing me back to what I could do with Hubble. So it's good, but it's not super. So of course, in space or on the moon, I would basically have like Hubble. Okay, no problem with that. And also another thing that I could do if I were in space is that I could build a Muse that probes also the other wavelengths that we have no access because of the screening of the atmosphere. So for instance, I could have a UV Muse. I could look at the UV lines, and so that will be actually quite good. There are plans to make a blue Muse now, but blue means, just down to probably 3,000 angstrom, not much more. So
I just love that name and everything about it. Blue Muse is phenomenal.
And it's important that we make the observation that as you've done, that adaptive optics is great, and in certain cases they can almost get Hubble resolution, but generally it works best at infrared, and it only works over a relatively small field of view.
Yeah, in fact, that's an important question, Frank. Sorry, is indeed this is a correction in the optical. At the end of the talk, I mentioned the symphony data. That indeed gave a great resolution in the infrared. So in the near infrared, you actually go almost as good as Hubble,
but not as good as James Webb yet, right? Well, and James Webb, of course, isn't quite, as I showed, isn't quite aligned yet. But when James Webb gets going, the comparison will then be, can we get as good as James Webb, right? All right, Grant, what's the next question?
Sure. That's a rotating theme, like getting away from interference from Earth, other sorts of things. This is more for you, Frank. Any plans for a deep field again from Hubble before we end life?
As far as I know, no. We have done the Hubble Ultra Deep Field 4 times, getting successively deeper and deeper in that area. Do not have I do not have the schedule for James Webb in front of me, but I really feel like one of the early observations is going to be a Webb deep field. Okay, and that's where we're really going to have new science coming up, is the comparison between the Hubble deep field and the Webb deep field. So we can look forward to that probably in the next year or so. Sometime
Yes. Soon.
Yeah. We'll see.
All right. This was going back to some of when you were explaining about the charts and all of our various axes of different information. When you're working with the globular clusters, what's the average size? Like, how many stars are in an average globular cluster that you were observing?
So a globular clusters, if I'm not wrong, packs up at most, 10 to the 6 a million stars, around a million stars, and it's all compacted. I think the half-light radius of globular cluster is typically around 5 parsec. So globular clusters are really, really dense. I mean, there's all sorts of funny things that actually happens in the center of globular cluster between stars, where actually stars do actually meet each other, unlike, in our solar neighborhood where stars are very far away from each other. So that's how compact it is. And yeah, this actually also helps in that, yes, we identify them with Hubble, but it also makes it easier to actually extract spectra, because even if with MUSE, even if we don't really resolve them, we know it's basically a point source, and then there is the galaxy background for the rest of the galaxy. So we essentially can just take the spectrum of the galaxy background and subtract it away, and we are left with mostly the central region where is dominated by the globular cluster light. So,
yeah, I would comment on the density of globular clusters. I once did a visualization of if our sun were located inside a globular cluster, and basically we astronomers would be out of business, except for stellar astronomy, okay? Because the whole sky would be covered with all this, or radio astronomy or something, because the whole sky would be covered with very bright stars, and it would be, we wouldn't see other galaxies very easily.
Talking about interference.
What's next?
All right. Oh, here's a good one. Is it possible to combine the IFS with radio interferometry? And how is it that we'll see the spectra of infrared? Or better yet, yeah. How do we combine IFS with radio interferometry? That's a good question.
Well, okay. So there's many well, we don't combine it directly, but we combine the information. And in fact, actually, one thing I forgot to mention in my talk is that I don't want to claim actually that integral-field spectroscopy is the first time that we are able to take spectra everywhere in a field of view or in the fuse region, because in fact, radio interferometry, radio astronomy has been doing this for a long time. The first rotation curves of galaxies were in fact worked out with radio astronomy. And in this case, they just follow one particular line from hydrogen. And likewise, when you go into Chandra or X-ray astronomy, so there you have each little photon, when it comes to the receptor, we actually tell its energy. So, and essentially, we know the energy of each little photon. So at every place, we actually have a small spectrum of just maybe 10 photons or so. But still, we have a spectrum everywhere. So a good example of how you combine information from radio astronomy and integral-field spectroscopy is maybe in a better understanding the accretion and of gas. So you can, with interferometry, or you can see the gas, the neutral gas, coming to the galaxy, and then as it goes to in the center of the galaxy, it becomes ionized because there are now stars that start to ionize the gas. And then later on, you can see if you actually go into the millimeter, what you see on the other hand is not the neutral gas, but you see the molecular gas, which is the part of the gas cloud that are very, very cold, and in the center, or first in Orion, only in the very center region, you have molecular gas. and that is actually the gas from which next you form stars. So you can see the neutral gas, then the ionized gas, and then in amongst this ionized gas, maybe in the spiral arms or maybe in the center, you actually find the very cold molecular gas. And the molecular gas and the neutral gas, you get it with interferometry from radio and millimeter observations.
All right.
I hope this helps.
Fascinating.
Well, I mean, it's something that we astronomers sort of take for granted, that we have these different variants in the interstellar medium. But showing how we get the observations that identify the different pieces of the interstellar medium is there's an awful lot of work to it. So I wanted to ask a question that combines two of your results. Okay, because when you were talking about star formation and you were doing the plots of the older stars versus the younger stars, and the younger stars were in the disk, and then the older stars, you got to about 10 to 14 gigayears ago, and they filled out the bulge and everything, right? So that sort of says, all right, the disk forms, about 10 gigayears ago. And then you came up with a MUSE result where you're looking out to redshift 1, and the disks were nice smooth rotation curves, 4 to 7 gigayears. So if we look at those two results, are we really started getting a feeling for when the disks form and when they become this nice smooth rotation, if we add those two together?
Well, I think that the images I showed you but that's one galaxy.
I know, different galaxies, right? And you have to do it in a statistical sense, but I was just...
But that's an interesting galaxy, because that's a galaxy that actually has a very nice characteristic, which is that it's basically an elliptical galaxy with a flat oblate main body and then a very thin disk.
Mm-hmm.
This galaxy is old. There is no ongoing star formation. And indeed, what you see is that, you have these disks. These plots I show you, they start at 3, 4, 5 gigayears, and then only at 10 gigayears. And I think, broadly speaking, is not too inconsistent. What we saw in the MUSE data for disks at redshift 1, so between 4 and 7 gigayears ago, is that already in place you have these nice disks. Okay, so that tells me that by that time disks were forming in a regular way. Maybe in this galaxy the disks formed earlier, but this galaxy, imagine that now, whatever galaxy is looking at that time, now you can form a disk. And these disks, they look thin, they look dynamically cold. They will look like normal disks. If you go back another 3 gigayears, and now you're 3 gigayears away from the Big Bang at redshift 2, things are very different. Then the disks are turbulent. They're much more disturbed. And so what is probably happening there is that you have a lot of star formation, and you may end up with a bulge instead, or with the thick disks. I think the jury is still a bit out, and exactly you can bridge the two, but it's not too inconsistent, I would say, the process. And that's what you saw also there, that the old stars are kind of there.
All right. Okay. So Grant, do we have time? We have time for one more question. Do you have a favorite one to pull?
No, there's been nothing more from the chat. You've answered everything.
Everyone asked about you answered the question that they want to know about Webb and the integral-field spectroscopy. So the Webb's IFS is going to be a small field of view, and it's not going to be that many pixels. I think, if I remember, it's like a 30 by 30 array for the IFS on Webb.
Yeah, what I know is that it's actually quite small, in the 3 by 3 arc seconds. So that really allows you to, for nearby galaxies, which are more I'm a redshift 0.1 guy,
Okay.
I'm a really, so it's really just looking at the center of nearby galaxies, or at, protoplanetary disks or things like this. But, this is really designed, James Webb was primarily designed to look back in time at the, origin of galaxies. So there's no problem with that. You will fill all these galaxies in. So that's why this was done.
And that's a really important point, is that, instruments are designed to address certain problems and not address every single problem out there, right? Especially when you're putting something on a space telescope, and it has to, it really has to pass the science reviews and everything for what is this telescope going to do? What problems is it going to answer? All right. So I guess the last comment I would have for you is the compliment on getting the acronym SAR on there so that you have the all-seeing eye for which to study the universe, right?
That was
That
the
was
idea.
impressive.
I don't even remember what it stands for, but it's basically, yeah, it was made up essentially. What it
All
does.
right. Well, thank you very much, Marc. Thank you much for joining us. I think it's been wonderful having a speaker from across the ocean to come and give our talk. This is so glad that you volunteered for this. Next month, April 5th, 2022, neutrino astronomy with IceCube. You gotta come. You gotta hear about how we do astronomy using these ghostly particles called neutrinos. Look forward to seeing you then.